Okay, so hi everybody, welcome back. What we're going to be doing today is starting a new chapter. That's chapter 15 of Giancoli, and the topic is mechanical waves. So as we start this new chapter, just keep in mind that we're going to be switching gears quite a bit. Up until this point, we've spent the entire semester covering thermodynamics. So all the chapters we've gone through so far are just different aspects of thermodynamics. Now we're going to start a whole new unit on waves. Okay, so let's start with the definition. What is a mechanical wave? What does that mean? So a mechanical wave is a pattern of oscillations in a material which moves through that material at a particular speed. Mechanical waves are always caused by some type of disturbance. By this we mean something that puts energy into the material and causes it to start oscillating. So we'll take a look at two examples here so you can get the idea down. First, if you look over here, at the bottom left of the page, what we have is a mass that bobs up and down in some water. So the disturbance is that mass bobbing up and down in the water. That's what's causing the wave to start moving. And the result of that is, again, this pattern of oscillations that you see on the surface of the water, and it's moving outwards at some speed. Okay, so that's the wave. On the other hand, if we look over here, this is an animation of a speaker and some air molecules nearby the speaker. So what happens when you have any type of speaker or even your headphones, the diaphragm of the speaker moves in and out in a regularly repeating sort of way, and it causes the air molecules nearby to start vibrating at that same frequency. And this pattern of oscillations of the air molecules is clearly moving outwards. That's what we call a sound wave moving outwards away from the speaker. So those are just two examples of mechanical waves. By the way, we're going to spend chapter 16, the next chapter, focusing entirely on sound. Okay, but it's an example of a mechanical wave. Okay, a little bit of terminology that we're going to see come up time and time again when we're dealing with mechanical waves. So we know that a mechanical wave moves through some type of material. What we call that material is the medium. Now, the medium can be a solid, a liquid, or a gas. Let's give some examples. So you could have a guitar string that's a solid material that can carry a mechanical wave if you pluck the guitar string. We also have the air, or the Earth's atmosphere. We know that can carry sound waves, so that's an example of a gaseous medium. And also, as I showed you before, the surface of a lake can carry waves along it. That's an example of a liquid medium. So there are all kinds of different examples of different mediums that can carry mechanical waves. Okay, when we talk about a wave moving through a medium, moving through some material, that's called propagation. So we say the wave is propagating through the medium. And again, depending on the situation, the speed of the propagation can be different. So a couple common ones that we want to know is sound waves propagate through air at about 434 meters per second. That's the speed of propagation of a sound wave through air. Light waves, on the other hand, propagate at a much faster speed through a vacuum, empty space. And that speed is 3 times 10 to the 8 meters per second. So those are some examples of the speed at which different waves propagate. Okay, some more terminology here. Sometimes the source of a wave can be a single disturbance that doesn't repeat itself. It just happens once and that's it. When that's the case, we call the wave a pulse. So let me show you an example of a pulse. Over here, we have a person's hand holding a rope, and if the person just moves their hand up and down once, that results in a pulse that moves through the rope. Let's take a look at what that looks like. So there's our pulse, right? We just have a single disturbance, again, the hand moving up and down once, that sends out a pulse through the string. On the other hand, if the disturbance repeats itself in a regular interval, then we get what's called a periodic wave. So the disturbance doesn't just happen one time, it repeats itself over and over again. That gives you a periodic wave. And over here, I'll show you an example of a periodic wave. Okay, so you see how the wave crests keep moving by the duck over and over again. in a regularly repeating pattern, that's called a periodic wave as opposed to a pulse. Okay. The next piece of terminology that we need to go over is something called the waveform. The waveform is the shape of the wave at any moment in time. Okay, so in other words, the shape of this pulse or the shape of this periodic wave, whatever that shape happens to be, is called the waveform. In this class, we're going to focus almost entirely on sine waves. In other words, waves that have a shape that just looks like the familiar sine curve that you've probably seen a million times before. So this is a sine wave. That's what we'll focus on as far as waveforms. Okay, so let's talk about some more terminology here. Let's talk about dissipation and dispersion. So dissipation is any process that converts wave energy into internal energy in your medium. So for example, if you had friction acting on your wave as it moves through a medium, that would convert the energy of that moving wave into internal energy in that medium. That would be an example of dissipation. Another thing we need to know is that in some cases, different parts of a wave can move at different speeds through your medium. That's called dispersion. So dispersion is when different parts of the wave move at different speeds. Okay, so those are the definitions. Let's take a look at this animation on the lower left, where I show you what it looks like if a wave moves with some dissipation. Okay, so the wave is losing energy as it moves, and the peak of that wave is getting smaller. That's what it looks like when you have dissipation. And eventually, that wave could just disappear altogether if it keeps dissipating energy. Okay, so that's what that looks like. Now dispersion, let's take a look at this animation over here. We have a wave with two peaks, and that wave is going to move to the right. But if the two peaks are moving at different speeds, in other words, we have two different parts of the wave moving at different speeds, that would be an example of dispersion. Okay? So the reason that we are talking about this is that we're going to make an assumption throughout the rest of this lecture. We're going to assume that there is no dissipation and no dispersion. Because if you notice, if we have dissipation, like in this animation over here, the waveform changes, the shape of the wave changes. And similarly, if we have dispersion, like in this animation, the shape of the wave also changes over time. So we're going to assume, to make things a little simple as we start talking about waves, that there is no dissipation and no dispersion, and therefore a waveform is not going to change its shape as it moves through a medium. It's just going to maintain the same shape as it moves. That will be the assumption we make. Okay, so I know that I'm really front-loading this lecture with a lot of definitions and a lot of different terminology, but this stuff is really important. If we're going to be able to talk about waves and communicate ideas effectively, there is some terminology that we just need to get down before we go any further. So the next thing to think about is a transverse wave. What does it mean when we have a transverse wave? Well, for a transverse wave, the oscillations in the medium are perpendicular to the direction of wave propagation. That's the definition. And we can understand this a little better if we look at an animation, okay? So what's going to happen in this animation is we're going to create a wave in this slinky here. That's going to be the medium. And the disturbance will be, we're going to shake it up and down at this end. That's what's going to create the wave. And let's take a look at an animation of that happening. Okay, so what I want you to notice is this. If you look at any given part of the slinky, it's being shaken up and down. So the oscillations in the slinky are up and down like this. But the wave is clearly moving to the right. That pattern of oscillations you see is clearly moving to the right. So in other words, the direction of the oscillations up and down and the direction of the propagation to the right are perpendicular to each other. And that's why we call this a transverse wave. Let's take a look at that one more time. Oops. So again, the slinky is oscillating up and down at any given point that you look at, but the wave itself is moving to the right. That's an example of a transverse wave. By the way, if you want to take a look at that animation again, I took it from this link that I put down here, so you can click the link in the lecture notes if you want to watch that again. And the last thing to mention about this is that a transverse wave is also sometimes known as a shear wave. These mean the same thing. Okay, so next, let's talk about longitudinal waves. So for a longitudinal wave, the oscillations in the medium are parallel to the direction of wave propagation. That's the definition of a longitudinal wave. So we're going to try to understand what this means by looking at an animation once again. And we'll have the same medium as before. That will be the slinky. But this time, instead of shaking it up and down like this, we're going to shake it from left to right, and that will be the disturbance that creates a wave in the medium. And this is what that looks like. Okay, so notice that if you look at any given part of the medium, any given part of the slinky, it's going to be oscillating from left to right like this, but the wave itself that's moving through the slinky is moving to the right. So therefore, the direction of the oscillations and the direction of the wave propagation, those are parallel to each other. Unlike before, when we had a transverse wave and they were perpendicular. Now they're parallel. That's what makes a longitudinal wave. So let's take one more look at that. Again, each part of the slinky is oscillating from left to right, and the wave is moving to the right. That's what makes a longitudinal wave. As before, if you want to take a look at this animation later, you can click the link that I put at the bottom of the slide. That's where I took this animation from. And the last thing to note is that sometimes you'll see a longitudinal wave referred to as a compression wave or as a pressure wave. So these all mean the same thing. These are just different ways of talking about a longitudinal wave. Okay, so with those definitions in mind, can you think of a few real-world examples of transverse waves? Can you think of some examples of longitudinal waves? So for each one of these categories, try to think of at least 3 examples of each type of wave. So pause the video, try to think of some of these examples, come up with a list, try to put 3 in each category, and let's see what you come up with. Okay, so I'll show you my own examples that I came up with for transverse and longitudinal waves. So you may have come up with a different list with different examples on it. That's fine. Let me just show you what I came up with. So one example of a transverse wave would be a wave on a string. So in other words, if you take the end of a string or a rope and you just sort of shake it up and down, you'll send a wave through the rope, and the direction of that wave motion will be perpendicular to the direction that you're actually shaking the rope up and down. So that would be a transverse wave. Okay? Another example of a transverse wave would be what we call the wave. Okay, the wave in a crowd, in other words. So if you've ever been to a big sporting event like a basketball or football game, sometimes the crowd will do the wave, and kind of sketch what that looks like. You'll have a person standing up at the sort of end of the wave, and another person standing up next to them. But if the wave hasn't reached the next person yet, they'll be sitting down like this. So in other words, the crowd itself, the people, are the medium, and they're oscillating up and down like this. But the wave itself is moving this way through the crowd. That's our propagation direction. And because, again, those are perpendicular to each other, we have a transverse wave. Okay, some other examples here. Light waves. These are also called electromagnetic or EM waves. So this includes the visible light that we see, as well as ultraviolet light and infrared light that we can't see. These are examples of transverse waves also. Okay, going on to longitudinal. If we have sound moving through air, sound waves moving through air, that would certainly be an example of a longitudinal wave. Turns out sound can also move through liquids and solids. So those would also be examples of longitudinal waves. And another example would be certain types of what we call seismic waves. These are the types of waves that you get during an earthquake. Specifically, I'm referring to what are called P waves. We're going to actually go over this in just a second. But the point is, certain types of seismic waves that occur during earthquakes are longitudinal. And actually, just as a bonus, there are other types of seismic waves which are transverse, and we call these S waves. So you can get both types of waves during an earthquake, in other words. So that's a list of some examples for you. Okay, so let's take this idea that we can have longitudinal and transverse waves and they have different properties, and let's use that idea to answer an interesting question, which is, how do we actually know that the Earth has a liquid core? So sort of a simplified model of the Earth that you should have in your mind is something like an onion. It has different layers, okay? And the layers may be made of different materials, but the outermost layers are all solid rock, whereas the innermost core of the Earth is liquid. In other words, the temperatures are so high in the core that what would normally be solid rocky material is now liquid. So how do we actually know that? It's not like we've been able to dig a giant hole that goes all the way to the core and just see directly that it's liquid. Okay, the reason we know this is a little bit more indirect, and it has to do with waves. So longitudinal waves can propagate through liquids, gases, or solids. On the other hand, if you have a transverse wave, it can only propagate through a solid medium. Okay, so in other words, if you have a liquid or a gaseous medium, it's not going to be able to carry a transverse wave. Okay, so that's just a fact that we'll keep in the back of our minds for what comes next. Okay, so in particular, I want us to think about what we call seismic waves. Okay, the type of waves that are created during earthquakes. So let's say the source of the seismic waves is an earthquake that happens over here. And what we're going to do is try to detect those waves at the polar opposite side of the Earth, so over here. Okay? Now we know that during an earthquake, you're going to have transverse waves that get sent out, and we call these S waves. You're also going to have longitudinal waves that get sent out. We call those P waves. Okay? So let's say we have a transverse wave that gets created over here. It has to move through the core of the Earth to get to the other side. But the thing is, a transverse wave cannot move through the liquid core of the Earth, so it effectively gets blocked, and we don't see it at the other side. On the other hand, if you have a longitudinal wave being created here, it can move through the liquid core of the Earth, and it can get to the other side. So that's exactly what we see when we study earthquakes, is that longitudinal waves can travel through the core of the Earth from one side to the other, but the transverse waves can't do that. They get blocked by the core somehow. The explanation for that is that the core is liquid, something that can only carry the longitudinal waves, but it can't carry the transverse waves, so those get blocked. The reason they get blocked is Earth has a liquid core. Okay, so next, we're going to do a quick review of simple harmonic motion, which is something that you learned back in Physics 45. And the reason we're going to do this is because simple harmonic motion is very closely related to wave motion, and we can use that as sort of a jumping off point to talk about wave motion. So let's start with a question for the class. The diagram shows a transverse sinusoidal wave on a rope. The wave is propagating to the right. Consider the particle on the rope marked with the red dot, this one right here. Which dot best represents where this particle would be located a short time later? In other words, is the red dot a short time later going to move to point A, to point B, or to point C? So think about this for a second, pause the video, see if you can come up with your answer, and then we'll go through it together. Okay, so the first thing to note here is that we're always assuming no dispersion and no dissipation in our waves, which means that the waveform itself, or the shape of the wave, is not changing. So it still has that sinusoidal shape that you see in the diagram. It's just that it moves to the right. In other words, if we want to understand what the wave looks like a short time later, the same exact shape that we saw before is there, just shifted over a little bit to the right. So I'm going to draw that same exact curve, shifted over to the right. So that would be our waveform a short time later. And of course, if we want to complete this, at the left side, we have to keep going down. So this is now where your hand is holding the rope. Of course, you're shaking the rope up and down to create the wave, so your hand has to move down a short time later. And the thing to notice is that the red dot just moved straight down. It did not move over to point B. It did not move to the left over to point A. It just moved straight down to point C. That's the part of the rope we're talking about. With the red dot, it moves straight down to point C. So the point on the rope in question moves straight down to point C. And this is a really important thing to remember about waves in general, okay? So the waveform itself propagates to the right, and that waveform can move a really long distance. It can move as far as you want. But parts of the medium, individual particles in the rope, let's say, are not moving large distances. In other words, this red dot is not really moving any distance left or right at all. It's just moving up and down. Okay, so individual points on the rope are just oscillating up and down. And they don't move large distances. Okay? In other words, the type of motion we're talking about, oscillating up and down, is called simple harmonic motion. So if we want to understand what any given part of the rope is doing, we can use what we know about simple harmonic motion to describe that. Okay, so that takes us to the relationship between simple harmonic motion and wave motion. And the idea is this: if we have a sine wave propagating in some kind of medium, the particles in the medium are not traveling over large distances, okay? Instead, those particles are undergoing simple harmonic motion. That is, they're oscillating around some kind of equilibrium position. So to give you a more concrete sense of this, I'll show you an animation where we have a sine wave traveling to the right on a string. And this blue dot just picks out a certain point on the string. And as we're going to see, even though the wave itself is moving to the right, that blue dot is not moving to the right at all. It's just oscillating up and down around some equilibrium position. So this is what it looks like. So again, this is a representation of a sine wave moving to the right on a rope or a string. And the blue dot, which just picks out a particular point on that string, is just moving up and down, up and down. In other words, it's undergoing simple harmonic motion. So that's the picture you should have in your mind. Now, that leads us to a question, because if the particles or the matter that makes up the medium is not traveling over large distances, what is traveling when a wave propagates? Something must be moving to the right. If it's not the actual material, what is it? So think about that question for a second, pause the video, and see if you can come up with some sort of answer to this. Okay, so what's the answer then? If it's not matter, if it's not particles that are moving long distances when you have a wave traveling through your medium, what is it? Well, the answer is energy. So when this sine wave moves through the medium, all that's happening to individual particles is that they're oscillating up and down like this. So they can't be moving over long distances. Instead, it's the energy carried by that wave that's moving. So we're going to get into the details of this later on, especially as we get to part 2 of this lecture. But for now, just keep in mind, it's not matter that moves over long distances when a wave travels, it's energy. Okay, so that brings us to the simple harmonic oscillator. So a simple harmonic oscillator, or SHO for short, is just something that oscillates back and forth in the way we described earlier. So every simple harmonic oscillator has certain features that we want to take note of. So first, we have an equilibrium position. That's just some position that our oscillator has where the force will go to 0. We also have what's called a restoring force, meaning if we take the system away from equilibrium, we displace it away from equilibrium by some amount, the force will bring it back to equilibrium. That's what's meant by restoring force. And that force is proportional to the displacement from equilibrium. So in other words, the more we take the system away from equilibrium, the further away we take it from equilibrium, the bigger the force will be to restore it back to equilibrium. Okay, and then finally, we have no energy loss through friction or air resistance. So that means once our system starts oscillating, it never stops and it never loses energy, okay? So the simplest example of that kind of system is a mass connected to a spring. That's what's shown right here. So we have a spring, the spring constant is K, and the mass connected to that is M. So of course we have what's called a restoring force, because we know that the type of force a spring will exert is given by Hooke's law. Okay, you may remember this from physics 45. The force exerted by the spring is equal to minus K times X. Okay, so if we want to sort of imagine what X is your displacement from equilibrium. So in other words, if X is equal to 0, you're right at equilibrium, there's no force acting on the block. But if I, let's say, stretch the spring out like this, then I'll have some positive value of X. And, well, if X is positive, then the force is negative, meaning the force is in the negative X direction, pulling us back this way. I could also imagine, if you wanted to, the spring being compressed. So we're over here somewhere, in which case X is negative. But if X is negative, we have a negative sign out front, that means the force is positive. So in other words, if I compress the spring, push the block in over here, the spring will be pushing now to the right in the positive X direction. So the point of this is to say it's a restoring force. The force exerted by the spring always pushes it back towards equilibrium. And again, that equilibrium position is X equals 0. So if we set the block in motion, maybe I pull the spring out this way and then let the block go, it's going to undergo simple harmonic motion, just oscillating back and forth like this, okay? Okay, so let's take a closer look at this simple harmonic oscillator. And in particular, let's apply Newton's second law to the block. So F equals ma. We can apply this to the x direction. So the net force in the x direction is equal to the mass of the block times the acceleration in the x direction. Now, the assumption is that we don't have any sort of friction or air resistance. So there's only going to be one force acting on the block. That's the one exerted by the spring, which is equal to minus k times x. Now, on the other side of the equation, we have mass times the acceleration in the x direction. So you should remember that acceleration is the second derivative of position with respect to time. So I can write this as d squared x dt squared, second derivative of position with respect to time. Next thing I can do is rearrange the equation. I want to take that negative term to the other side, and I'm going to divide through on both sides by m. So I'm going to be left with second derivative of x with respect to time plus k over m times x equals 0. Okay, the next thing I'm going to do is I'm going to define a constant called omega, where omega is equal to the square root of k divided by m. So therefore, my equation looks like this. I have the second derivative of x with respect to time plus k over m, which would be omega squared, given the definition of omega that I just wrote down, times x. And that is equal to 0. Okay, so we'd want to solve that differential equation, this one in the box, to get x as a function of time. Okay, and my claim is the general solution for x as a function of time is this. X as a function of time is equal to a times cosine omega t plus phi, where a, phi, and omega are constants. So this is what I claim is the general solution for the position of the block as a function of time. So what I'm going to do next is just show you that it works. So first, if this is truly the solution for x as a function of time, I could take the derivative of that and get dx dt. And okay, so I'm taking the derivative of that function I just put in the box. First thing to remember is I have a constant out front a. And then if I take the derivative of the cosine function, I'm going to get minus sine of omega t plus phi. But the thing is, I also need to take the derivative with respect to time of what's inside of the sine function. And basically, that's just going to give me omega, because the derivative of omega t is just omega, and then phi is a constant, so that doesn't even come into play. Then, if we take the second derivative of x with respect to time, that's just the derivative of this guy. So I'm going to have a omega as two constants out front. Now, when I take the derivative of sine, I get cosine. But I already had the negative sign out front, so now I have cosine omega t plus phi. But again, I have to take the derivative of what's inside, which brings out a factor of omega. So now I have omega squared out front. And let's just check to see that it solves the differential equation we wrote down. Because remember, the second derivative of x with respect to time plus omega squared times x, that should equal 0, according to our equation. And we just said the second derivative is minus a times omega squared times cosine omega t plus phi. And then I have omega squared times x by itself, which is what we started with. So I have here a cosine omega t plus phi multiplying that. And then it's pretty obvious that if I add those two, I get 0. So the solution works. So we know that for a simple harmonic oscillator, this is the general form of the solution, a times cosine omega t plus phi. Okay, so let's take a closer look at that general solution for the position as a function of time of a simple harmonic oscillator. So we have x of t is equal to a cosine omega t plus phi. Now we have three different constants in there, which are the amplitude a, the phase angle, that's what we call phi, and the angular frequency omega, which as we said is root k divided by m. Okay, so in a nutshell, what the amplitude tells you is the maximum displacement from equilibrium that your system ever reaches. So if we plot x as a function of time, so I have x, that's position on this axis, and then t, that's time on this axis, a just tells me the maximum value of x that I reach, and of course I'll reach it in the negative direction as well, so I'll also have negative a on the other side. Now, what about the phase angle? Well, the phase angle just takes this general curve we have here, and it shifts it either to the left or to the right on the time axis. Okay, so all that phi does is it shifts your function to the left or the right to match whatever initial conditions you might have. Now the angular frequency tells you how fast does the system oscillate. So if omega is bigger, the system oscillates much faster. If omega is smaller, it oscillates much slower. So to give you a visualization of this, okay, what I'm going to do is show you an animation of the mass going back and forth like this, and then we'll trace out the position on this graph as the mass oscillates back and forth. So here's what it looks like. So we'll see that again. So we start off at plus a, then to negative a, then back to plus a, back to negative a, then back to plus a. That's the oscillation that's happening to this system. Okay, and again, a represents the maximum displacement. Okay, now what about energy in simple harmonic motion? Well, the total mechanical energy, which we call E, is the sum total of potential and kinetic energy. In other words, E is equal to K plus U. And since we're assuming that there's no friction or air resistance to speak of, once we set our system in motion, mechanical energy is going to be conserved. Okay, so when we say E is equal to K plus U, there are two parts to that. We have kinetic energy equaling 1/2 mv squared, and we have U, potential energy, equaling 1/2 kx squared. That's the spring potential energy function. That's something we learned back in physics 45. So what I want to show you is that the total energy E can be expressed purely in terms of the amplitude of the motion. So in other words, if we do a little work, we can show that the total energy E is equal to 1/2 k times a squared, where a is the amplitude. So let's see how that works. Okay, so we'll start with this. We know that the general solution for x as a function of time is equal to a times cosine omega t plus phi. And so therefore the velocity v, which is the derivative of position with respect to time, so that's dx dt, that would just be the derivative of this function here, which we already worked out, but it's here, minus a times omega times sine omega t plus phi. And so therefore the total mechanical energy we use E to represent that, which is equal to K plus U, gives us this. We have 1/2 mv squared for the kinetic piece, and then we have 1/2 kx squared for the potential. So we'll just directly substitute the velocity and the position that we just worked out. So E is equal to, I've got 1/2 m. Now my velocity is minus a omega times sine omega t plus phi. We have to square that velocity. And then I have plus 1/2 k times x, which is a cosine omega t plus phi. And I have to square x as well. Okay, so looks like we have some common factors here. We have 1/2 and we have a squared in both terms if we factor that out. Now, in my first term, I'm going to have an m factor and an omega squared factor. And since we have a negative that gets squared, the negative sign goes away in this first term. So we have m times omega squared, and then sine squared of, I'm not even going to write this again, it's omega t plus phi, but you know what's inside the sine function, so I'll just put ... And okay, in the second term, we already pulled out a factor of 1/2 a squared, so all that's left is k. And then we have cosine squared, the same thing. I'll just write ... like this. Okay, so the next thing I want to remind you of is that omega is the square root of k over m, which means if we square both sides, we have omega squared is k over m, or m times omega squared is equal to k. In other words, this term right here, m times omega squared, I can just replace it with k, which means actually both of these terms just have a factor of k that I can pull out, so I'm going to do that. Now it's 1/2 k a squared out front. And the first term is just sine squared, and the second term is cosine squared. And the trig identity that you should be thinking of is if we have sine squared plus cosine squared of any angle whatsoever, that's just equal to 1. So we're left with 1/2 k a squared. Now notice these are all constants, so the total mechanical energy is conserved. The idea is we came up with this formula for the total mechanical energy, and it just turned out to be a constant, something that doesn't change over time. That's just another way of saying it's going to be conserved. Okay, so let's take some of those energy ideas that we've been working with and use them in an example problem. So here we have the simple harmonic oscillator consisting of a block with a mass m, which is equal to 1.75 kilograms, connected to a spring with a force constant k equal to 354 newtons per meter. The block oscillates back and forth with an amplitude of 5.18 centimeters. What is the total energy of the oscillator in joules? And what is the maximum speed of the block in meters per second? So try to work this out, pause the video, see what you get, and then come back to it so we can do it together. Okay, so first, we're going to use the fact that the total mechanical energy can be written as 1/2 k a squared. And there's a little trick with the units that I want to show you. So for k, we measure this in newtons per meter. But remember, a newton is a kilogram times a meter per second squared. So we're going to divide that by meters, and we'll just be left with, after canceling out meters, kilograms per second squared. So for energy, I have 1/2 k, which is 354, and we'll write this as kilograms per second squared for the units. Then 5.18 centimeters would be 5.18, 10 to the minus 2 meters, square that. And if you do the calculation, you'll get 0.4749 We have kilograms, meters squared per second squared. We'd want to keep 3 sig figs on that. And by the way, this unit that we're left with is a joule. So what we have is 0.475 joules. Okay, next, we know the amplitude. So in other words, we know that the maximum displacement from equilibrium is 5.18 centimeters. But we also want to know for this follow-up what the maximum speed is. So here's how we'll do that. Remember, this energy is kinetic plus potential. So the total energy E is conserved, but K and U can be changing individually. It's just the sum total that has to be the same at all times. So basically, if we want K to be as large as possible, we want U to be as small as possible. So the potential energy should equal 0 when kinetic energy is at a maximum. Okay? So therefore, E is equal to, the maximum kinetic energy would be 1/2 m v max squared, where that's the maximum speed squared now. And we set potential equal to 0 because that's as small as it can get. That will give us the largest kinetic energy. So V max squared is going to be 2E divided by m. So of course we want to square root that to get V max. So I'll have the square root of 2 times E, which is 0.4749 joules, which again is a kilogram meter squared per second squared, divide by the mass, which is 1.75 kilograms. Cancel out kilograms. If you do this calculation, you will get 0.7367. Units are meters per second, or rounding it off, 0.737 meters per second. So that would be the maximum speed of this oscillator. So next, we need to figure out how to mathematically describe a wave. Now, the simplest case we can look at is a sinusoidal wave in one dimension. So remember, sinusoidal, this means the shape or the waveform is just a sine curve. And one dimensional means the wave only moves in one dimension as opposed to 2 or 3. So we have to think about this general problem of a sinusoidal wave traveling in a one-dimensional medium. So to give you something to think about, let's say this represents a string. This line here represents a string or maybe a rope of some kind. And we know that if we were to create a wave in the rope, it could only really move to the right like this or to the left like that. So that's a one-dimensional medium because your wave can only move in one dimension. So we don't want to be too much more specific than that because we can think about a transverse or a longitudinal wave in this one-dimensional medium. So the idea would be this line is the x-axis. This tells us the direction that our wave propagates. So it can propagate in the positive x direction, or it can move in the negative x direction like this. However, if we look at a particular part of the medium, it's going to be oscillating up and down in some way. And so the displacement d, if we have a transverse wave, is going to be perpendicular to the direction of propagation. So that's what makes a transverse wave, is the fact that the wave is being displaced this way, but moving this way. On the other hand, if we had a longitudinal wave, then our displacement would be parallel to the direction of propagation, so it would be along the x-axis. You would be oscillating back and forth this way. Okay, so if we have no disturbance in the medium at all, then every single particle is just going to remain in its equilibrium position. There's going to be no wave at all moving through the medium, so no displacement at any point. D is just equal to 0 everywhere. However, if we do have a disturbance, then we're going to have displacement away from equilibrium. Now, if the disturbance is sinusoidal, meaning if you want to picture holding the rope at this end and shaking it up and down in a sinusoidal sort of way, then the particles in the medium are going to undergo simple harmonic motion. They're going to vibrate or oscillate back and forth in simple harmonic motion. So that's what we should be picturing here as far as our wave. Now, if we want to fully describe the wave, what we need is d, the displacement, as a function of x and t. So in other words, why is it a function of x? Because, of course, you could have a different displacement over here than you have over here. So it's going to depend on your position. The displacement of the wave is going to depend on your position x. On the other hand, it's also going to be a function of time, because if you look at a fixed position, the displacement might be changing over time. And in fact, if it's oscillating up and down at a particular position, then of course your displacement is also changing over time. So what we need is this function. How does our displacement depend on x, position, and t, time? Okay, so let's take a look at some characteristics of sine waves and how we can understand them better by looking at graphs. So I have two graphs here to show you. They look kind of similar, but they're conveying different information. Okay, so if we look at the graph on the left, this is a snapshot of what a sine wave looks like at a particular instant in time. So we're going to fix t at some fixed value. For instance, you could have t is equal to 0 as an example. So quite literally, you can think of this sine wave as traveling to the left or to the right, but then just taking a picture of it at one moment and sort of freezing it in time. This is what it would look like. Okay, so what we're plotting here is the displacement of our wave d as a function of x, that's on this axis, and then x, that's position on this axis. So of course we have this sinusoidal shape, and we can take note of a few things. What we call the peak of the wave, where it's at its highest point, is the crest, and then the lowest point is what we call the trough. And we can pick out the amplitude, the maximum displacement from equilibrium, just by looking at how high the crest goes for our wave. So in other words, if we start here at 0 displacement and then just work our way to the crest of the wave, that's the amplitude A. That's the maximum displacement from equilibrium. On the other hand, if we look at the distance between two crests, so I'll have my wave peaking over here, and then another crest over here, there's some distance between those 2 points. And that's called lambda, or the wavelength. Okay, so that is a distance in space. That's lambda. Okay, now let's take a look at the graph on the right side. So this is showing you a particle at a fixed position. So we're going to fix the value of x now. So maybe x is equal to 0. And look at how it moves around. Okay, we know it undergoes simple harmonic motion. So in other words, the displacement is now a function of time because we're keeping x fixed. So we're letting t be the variable. And then time t is now on this axis. And so what is a particular particle in our medium doing? It's undergoing simple harmonic motion, so it looks like a sine curve also, just like this. And of course, we have the trough and the crest, and the amplitude is just how high that crest goes. But now, if we look at the distance from one peak of the wave to another, or one crest to another, now this is an amount of time, okay? That's the amount of time that passes between this moment and that moment. And what we call that is the period. That's the time it takes this particle in our medium to undergo one full oscillation. So here, think about this. It starts at equilibrium, reaches maximum displacement. We go down to negative A, and then back up to our maximum displacement, and then we just repeat that. So of course, the amount of time it takes to undergo that one full oscillation is called the period. We use capital T for that. Okay, so let's talk a little bit more about some characteristics of sine waves. Next, we have the frequency. So the frequency of a sine wave, given by f, lowercase f, is the number of complete oscillations a particle completes per unit of time. So the SI unit here is going to be hertz. 1 hertz is equal to 1 cycle per second. That's the definition. Now, the way frequency relates to period is actually pretty simple. Frequency is just 1 over the period, or the inverse of t. Okay, next. In one period, so if we're looking at one period of the wave, any part of that waveform is going to move a distance equal to the wavelength. And because of that, we can derive a fundamental relation between the frequency, f, the wavelength, lambda, and the speed that the wave is propagating with, v. And here's the fundamental relation. V is equal to lambda f. So before we go any further, let's just derive these two formulas. Okay, so we'll start by saying that the period is the time it takes to undergo one cycle. And the frequency, as we just defined it, is the number of cycles that you undergo in every unit of time. So just by looking at these definitions, it should be pretty clear that one of these is just the inverse of the other. So in other words, frequency is just the inverse of the period. So for example, let's say the frequency in question is 10 hertz. That would imply that the period is the inverse of that, so 1 over 10, or 0.1 seconds. So if it takes 0.1 seconds to complete a cycle, that's what the period is, then we're operating at 10 cycles every second, or 10 hertz. Okay, that's the relationship. Okay, next. The speed of the wave should be the distance the waveform travels divided by the time. So if we have a sinusoidal wave, something like this, that's our waveform at one moment in time, but in the next moment, it might have moved over some amount. So here, this point that I'm labeling with a little x on my waveform might be over here now. And so this little dashed line represents where the wave is in the next moment. Okay? So what distance has the waveform moved? Well, this is one wavelength. But if I ask how long it takes to do that, how long did it take for the waveform to move over that far? Well, the time is one period. So if you look at any given point on the wave, let's say over here, in the time that's elapsed, it will have moved up and down through one full cycle, through one full period to get back to where it is. Okay? So speed is given by v, the distance is lambda, and the time is one period, capital T. But remember that the period t is the inverse of the frequency, so I can write this as lambda times f. So therefore, v is equal to lambda times f. That is the fundamental relationship between the speed, wavelength, and frequency of a wave. That's where it comes from. Okay, so now that we have this fundamental relationship between speed, wavelength, and frequency, let's do an example problem. So a radio wave with a frequency of 93.5 megahertz travels at 3 times 10 to the 8 meters per second. So that's the speed of light. The question is, what is the wavelength of this wave? So by the way, this is a radio station broadcasting out of Los Angeles. I think it's called K-Day. That's the frequency of the wave. So from that and the fact that you know the speed, try to figure out the wavelength of this radio wave. So pause the video, see if you can work this out, and we'll go through it together after you have your answer. Okay, so we have V is equal to lambda F, and we're going to sort of flip that around to solve for lambda. We want to know the wavelength, which is V divided by F. So for V, we have 3.00 times 10 to the 8 meters per second. For F, we have 93.5 megahertz. So that mega prefix is 10 to the 6. So 93.5 million, in other words. And hertz is just the same as inverse seconds. So what we're going to be left with after canceling out the seconds is just units of meters. And if you do the calculation, you'll get 3.21 meters. So that's a pretty big wavelength for your typical radio station that you're picking up, driving in your car or whatever. About 3.21 meters in this case. Okay, so next we'll go over some more sine wave characteristics. And we'll start with the angular frequency. That's given by omega. Now, angular frequency is really similar to just the normal frequency F. The only difference between the two is that instead of measuring in cycles per second, so saying how many cycles does our wave undergo every second, we're going to measure this in radians per second. So they both quantify how fast the wave is oscillating. It's just a matter of whether you want to do that in cycles per second or radians per second, okay? So for omega, we're doing radians per second. So omega, therefore, is equal to 2 pi times F. There's only a factor of 2 pi differentiating the two. The next thing that we're going to get into is the wave number. So the wave number is given by a lowercase k, and the units are radians per meter. Now, we're not even going to derive this. This is just something that we're going to define. K is equal to 2 pi divided by lambda. That's just the definition of this new quantity that we call the wave number. There's nothing really more to it than that. So K is 2 pi divided by lambda. And of course, we can relate this to the speed of propagation V, just like we did before. And the relationship there is now V is equal to omega divided by K. So the relationship between the angular frequency omega, the wave number K, and the speed of the wave, V, is equal to V is omega divided by K. So again, let's just quickly derive all of this and then go to the next part. So to show you where that first result came from, let's say we have X cycles per second. So we have something oscillating at some number of cycles per second, whatever that happens to be. If we wanted to convert that to radians per second, we'd have to multiply by a conversion factor, which says that in every 1 cycle, we have 2 pi radians. And now the unit we're left with is radians per second. And to get there, we had to take what we started with and multiply by 2 pi. So the point of saying all that is, if we want omega, but what we know is F, we just need to multiply by 2 pi to go from one to the other. And of course, we found earlier that V is equal to lambda times F. Well, from what we just wrote down, F is equal to omega divided by 2 pi. We also know that K, the wave number, is equal to 2 pi divided by lambda, meaning lambda is 2 pi divided by K. So therefore, V is equal to lambda, which is 2 pi divided by k, and multiplied by F, which is omega divided by 2 pi. That gives us the second result, which is V is equal to omega divided by k. So that's where those results came from. Okay, so next I want to sort of quiz you on something really quick that you should have seen in a math class at some point, which is how do you take a function and then shift it along one of the axes? How does that actually work? So the curve shown on this graph here is the function f of x is equal to x cubed. So that's just the function x cubed when we plot it out. So what if I wanted to show the same exact curve, but shifted 3 units to the right? So now it's over here somewhere. How would I do that? Would f of x be equal to x cubed minus 3 like this? Would it be x cubed plus 3 like this? Would it be x plus 3, that whole thing cubed? Or would it be x minus 3, that whole thing cubed? So which one of those options shows us the function being shifted 3 units to the right along the positive x direction? So pause the video, think about it for a second, and see if you can come up with the right answer, okay? Okay, so let's go through all these different options. Let's start with answer choice A. This says f of x is equal to x cubed minus 3. That's not correct. That's actually going to be the same curve shifted down 3 units. So it would be down here somewhere. Answer choice B, x cubed plus 3, that would shift the curve up 3 units like this. So that's not what we want either. Answer choice C also doesn't work. If we add 3 to x and then cube, we're actually moving the function to the left like this by 3 units. So if we want to actually move in the positive x direction 3 units, we have to subtract 3 from x and then cube, so we're over here. In other words, I need to replace x by x minus 3 to show that we've moved the graph over to the right by 3 units. Okay, so this is how it works. Okay, so now we're ready to come up with this function d of x and t, so the displacement as a function of position and time for our sine wave. And what we're going to be considering generally is a sine wave with an amplitude a. And let's say for now it's moving in the positive x direction at speed v. So it's moving this way to the right at speed v. So we'll start by saying what the wave looks like at a particular snapshot in time, let's say at t is equal to 0. So instead of d as a function of x and t, we're going to just plug in 0 for the time. So we have d as a function of x, and then setting the time equal to 0, that's equal to a sine kx. So before we go any further, I want to show you where this comes from. Okay, so I'm going to start just by showing you why this works, why this describes the snapshot of our wave at t is equal to 0. And the way we're going to do this is by just testing out some points. Okay, so at t equals 0, we have d as a function of x is equal to a sine kx. And we'll remember that k is equal to 2 pi divided by lambda. Okay, so what if I plugged in x equals 0? This would say that the displacement at x equals 0 is equal to a times sine, well, I'm just plugging in 0 there, so what I get out is 0. Now, does that actually work? If we go to the graph, remember, this is x equals 0, and the displacement is 0 from the graph, so that seems to work. Okay, what if we plug in x equals lambda divided by 4? So here, if we start here at x equals 0, and we go a quarter wavelength, so we'd be up here now, because this is a full wavelength. So we'd be at this peak or this this crest of the wave right here at a quarter wavelength. So the displacement at x equals lambda over 4 is equal to a times sine, okay, k is equal to 2 pi divided by lambda. X is equal to lambda divided by 4. So we have a times sine. Pi over 2 is what we're left with. Sine of pi over 2 is 1. So this is a. That's telling us that at a quarter wavelength, we should be at the amplitude of the wave, the maximum displacement, and that is true if you look at the graph, okay? So what if we say x is equal to lambda over 2? So half of a wavelength. Now we're over here. And according to our function, if I plug in half of a wavelength, so lambda over 2, I'm gonna get a times sine of k, which again is 2 pi divided by lambda. But now I have lambda divided by 2 for x. So I have a times sine of pi, which gives me 0. Okay, according to the graph, again, right here, at half a wavelength, we're at displacement of 0. So that also works. What if x is 3/4 of a wavelength? So here, now we're at this trough down here. Then the displacement at x equals 3 lambda over 4, 3/4 of a wavelength, is equal to a times sine. We have 2 pi divided by lambda, and then 3 lambda divided by 4 for x. So again, that's just k times x. That equals a times sine, and then what we're left with is 3 pi over 2 when you plug that in. Now, sine of 3 pi over 2 is minus 1. So we should be at minus a, or the minimum displacement, which is definitely the case because we're at that, again, trough of the wave down here. So that works. And then finally, if we say x is equal to lambda, so we go a full wavelength, the displacement at x is equal to lambda should be a times sine. K is 2 pi divided by lambda. And now I'm just plugging in straight up lambda right there for x. So now we have a sine 2 pi. Sine of 2 pi is back to 0. So is that the case? After one wavelength, are we at 0 displacement? Yes. Yes, we are. That's where we are after one wavelength. So the point of all this is that this works. It describes the wave we're looking at. And so then we can go from there. Okay, so this describes what the wave looks like at t is equal to 0. It's given by a sine kx. That describes this snapshot of the wave at t is equal to 0. But what happens a short time later? Well, a short time later, this overall waveform that you see here is going to move to the right, since we're assuming we're moving in the positive x direction, by some distance. And the distance you move is equal to the speed, which is v, times the time, which is t. So this is the distance that our waveform is going to shift over to the right by, v times t. So we can show that on the graph. This is the new snapshot of the wave, the one shown in a dashed line, a small time later. And again, it's moved to the right a distance v times t. Okay, cool. But how do we actually indicate mathematically that a curve has shifted over to the right? Well, this is exactly what the previous question was asking about, right? We're going to replace x with x minus vt. That's how we implement the shift. Again, if we want to shift it to the right, we need a negative sign here. If we were to shift it to the left, we'd have a positive sign here. But since we're assuming we're moving to the right, this would be x minus vt. So in other words, what we had previously was just a sine kx. Now we're going to have a sine k times the quantity x minus vt. Okay? And what we learned earlier is that V can be written as omega divided by K. So if I replace the V right here with omega divided by K, well, the K on the bottom here is going to cancel with this K, and I'm just going to be left with omega. So in other words, I'm going to have A times sine of Kx minus omega t. This is how I describe a traveling wave moving to the right. Okay, that's how it works. Okay, so we've arrived at a really important result, which is the general expression for the displacement of a sine wave that moves in one dimension. So here it is. We have d as a function of x and t, that's the displacement, as a function of position and time. That equals a sine kx minus or plus omega t plus phi. All of that is inside of the sine function. So the reason there's a minus or plus sign here is it depends on which way the wave is moving. We saw earlier that we're going to choose minus omega t for a wave that moves in the plus x direction, but if we were moving in the negative x direction, then we would choose plus omega t. That's how you interpret this part of the expression. Now the phase angle, which we didn't account for before, it basically just allows you to shift the function to match the initial conditions. So in other words, our wave, whatever it happens to be, is going to have some displacement when you set t equals 0 and x equals 0. And you just want to be able to match whatever that displacement is for the situation you have. The way you do that is just by choosing the right value of phi. So let me give you a couple examples here. On the first graph, what you're looking at is displacement as a function of x, but we fix the time to be t equals 0. And so it looks like this. Okay, in the second example, we have displacement as a function of x, just like before, at a time fixed at 0, but now this is what our sine wave looks like, okay? So the difference between the two is you see one is shifted along the axis differently than the other, and so they have different phase angles, they have different values of phi. So in the first case, we have phi is equal to 0. In the second case, we have phi is equal to pi over 2. Let me explain how I got these numbers. Okay, so in the first example, let's label this one number 1. We know that our displacement when x is equal to 0 and t is equal to 0 is, well, go to the graph. This is x equals 0. So it looks like we have 0 displacement right there at that point. And remember, this function is a times sine of kx. So I'll say k times 0 because x is equal to 0, plus omega times time. And again, omega is equal to 0 here. And then plus phi. Okay, all of that is equal to 0. Okay, so a times sine of phi is equal to 0. In other words, sine of phi is equal to 0 in that first example. Well, what angle do you take the sine of and it gives you 0? Well, 0 would be the answer to that. So that's why we say phi is equal to 0 in this first case. In other words, it's just a regular sine curve. It's not shifted either way along the axis. On the other hand, in the second example, number 2, we'll play the same kind of game where we have d at x equals 0 and t is equal to 0, and then from the graph, we'll determine what that is. So again, we're already looking at time is equal to 0. We just need to look on the x-axis and choose x is equal to 0. So that's up here. So the displacement is not 0. In fact, it's the maximum value. It's a at that point. And so we have a sine times kx, so k times 0 once again, plus omega t, t is equal to 0, plus phi, and that's now equal to a. So we have a sine, all this is 0, so we just have sine phi. That's equal to a. So therefore, sine of phi is equal to 1. So then again, the question becomes, what angle do we choose where the sine of that angle is equal to 1? That's pi over 2. So this is not just a regular sine curve. It's shifted by pi over 2 in the second example. And again, the point is the angle phi allows us to do that. So that's going to be it for this lecture. I'll see you in the next video. So until then, as always, take care. See you later.